Welcome to video 2 of chapter on combustion turbines. We're going to pick up here on continuing an analysis on isentropic processes. So now what we're concentrating are on the compression process right now. So if you remember, at the end of the prior video, we went ahead and covered how to evaluate the isentropic efficiency of a compressor and also a turbine. So I'm going to go ahead and just look at a diagram real quick for both, first a compressor and then a turbine. And we're going to do an example problem for each, just again to make sure that we drive this point well. So looking at, this is a TS diagram. So if we were actually to go back and look at only this point, right, this is the compression process for the Brayton cycle. This is the isentropic version. So if we're actually going to take this part of this diagram and blow it up, we would end up with, right, this part of the diagram here is represented, that part of the diagram is represented right here on this graph, right? So again, temperature, y-axis, entropy, x-axis, state 1 coming into the turbine, into the compressor, state 2 coming out of the compressor. This is the isentropic process. This is what we would call the upper pressure line. This is what we would call the lower pressure line. So these two lines represent what constant pressure looks like on a TS diagram. So this is the pressure entering the compressor. This is the pressure exiting the compressor. So from state 1 to state 2, you can see it's an isentropic process, constant entropy. Now, just to kind of illustrate, again, this is what we would call the isentropic work, right? The amount of work between the state going in and out of the isentropic process. Now, as the process becomes more non-isentropic, entropy is produced. So what's happening is that you actually have an entropy state higher coming out than it is going in. So state 2 here represents a state 2, the actual state 2, coming out of the compressor if the process were to be non-isentropic. And you can see that you want to come out on the same pressure, right? So again, the pressure constant pressure line kind of curves up. So as you can tell, you're coming out higher here on the pressure line, which means that the temperature coming out of the compressor during the non-isentropic process is actually higher than the temperature coming out of the compressor if it were isentropic. Basically what's happening is that all of the work that doesn't go into pressure change goes into increasing heat, right? Increasing the temperature of the gas coming out. So what you end up with is, this is the representation, this vertical distance between the state going in and out kind of is a representation of the amount of actual work going in. To drive that home a little bit, let's go ahead and just do an example problem from your book. So the example problem here reads that air enters the compressor of a gas turbine engine at 100 kPa and 300 Kelvin. If the compressor ratio is 8 and the isentropic compression efficiency is 0.87 or 87%, wants you to find the following. A, the exit temperature and pressure of the air from the compressor, the work per unit mass added to the air by the compressor, and the exit temperature of the air if the compression process were isentropic. So let's go ahead and let's first write out our efficiency equation. Again, this is assuming constant specific heats. We get that the efficiency is going to be the isentropic temperature coming out of the compressor minus the temperature going into the compressor divided by the actual temperature coming out of the compressor minus the temperature going into the compressor. Now, what the problem's asking for is these two exit temperatures and wants you to solve for those. It also wants you to solve for the so what we're going to actually do is we're going to solve for the temperatures coming out, the isentropic and actual temperature, and we're also going to look at the compressor work. So first off, this one's pretty straightforward to compute, the isentropic temperature. So the isentropic temperature coming out divided by the isentropic temperature going in is equal to the pressure ratio, so P2 over P1, to the K minus 1 over K. Now, normally for air, the specific heat ratio, right, which is Cp over Cv, or K, is about 1.4. So if we were to solve for that, T2 isentropic is going to equal the temperature going in, which is 300 Kelvin, multiplied by the compression ratio, which is 8, raised to the K minus 1 over K. So in this case, we would get that the isentropic temperature coming out is 543.3 Kelvin. And with that now, we can actually use the compressor efficiency, which is 0.87, right? And we can actually use that to compute what the actual temperature coming out of the compressor is. So again, that would be 0.87 is equal to T2S, 543.3, minus T2 in, minus 300, divided by the actual temperature, which we're trying to compute, minus the temperature going in. Set up your algebra, you get that the actual temperature coming out is 580 Kelvin, again, which is higher than the isentropic version. Lastly, the problem's asking you to compute the compressor efficient, or the compressor work, right? So the actual compressor work, so per unit mass. So that would just be delta H, or CP delta T actual, right? So if you plug that in, CP for air is about 1 kilojoule per kilogram Kelvin, multiplied by the temperature difference gives us a compressor work per unit mass of 280 kilojoules per kilogram. So again, that's just a quick example problem to kind of, again, it's a review because we did this in thermodynamics of how to treat isentropic efficiencies of compressors. So now that we've done that, let's go ahead and do the same thing for the turbine. So again, the turbine is just going to be the opposite. So if we look at back at this TS diagram of the ideal Brayton cycle, we're going to take the expansion process 3 to 4, take that, and then focus in on that part, blow it up on a chart. So again, this is temperature on the y-axis, entropy on the x-axis, two constant pressure lines, right? These P3 is the temperature going into the turbine, P4 is the temperature coming out of the turbine. So here we have T3, isentropic process, comes out, T4 isentropic, where the length of that line is sort of a representation of the vertical length of that line is a representation of the isentropic work. But again, as inefficiencies are present, entropy coming out is going to be higher coming out than in, right? So here's S1, or sorry, S3, here is S4, right? So the actual temperature, T4 actual, will be less than T4 isentropic because of some of the work that you lose. So again, this vertical kind of line representation is a representation of the lesser actual work compared to the isentropic. So again, where the turbine efficiency in this case would be that actual work divided by isentropic work. And assuming constant specific heats, you can basically reduce this equation down as a function of temperature. What would be the temperature in minus the actual temperature out, divided by the temperature in minus the temperature going out if it were isentropic. So to drive this point home, let's just go ahead and do an example problem for this one. So this example problem from your book reads, the inlet and outlet absolute pressures for the turbine section of a gas turbine engine are 550 kPa and 100 kPa respectively. If the turbine inlet temperature is 1000 Kelvin and the isentropic expansion efficiency is 91% or 0.91, compute the following. So we're going to compute the turbine exit temperature and the work per unit mass extracted by the turbine. So again, I'm going to start off by writing my equation for the isentropic efficiency of a turbine, assuming constant specific heat. So again, that would be T3 minus T4 actual over T3 minus T4 isentropic. So we're trying to find out what this T4 actual is. So before we do that, let's do T4 isentropic. So we have T4 isentropic over T3 is equal to the exit pressure divided by the inlet pressure to the K minus 1 over K. Again, in this case, what we're going to do is we're going to assume the specific heat ratio to be 1.33 as opposed to 1.4. Why? Because as the temperatures of the air going into the turbine are significantly higher than the temperatures of the air going into the compressor. And so what you would do is if you were to look up the specific heat ratio, you can see also that that has some change with temperature. So when you're dealing with temperatures around 1,000 Kelvin, the specific heat ratio decreases a little bit. So assuming that to be the case, we can go ahead and compute that. So we get T4 isentropic will equal the entering temperature, which is 1,000 Kelvin, multiplied by the pressure ratio, which would be 100 kPa over 550. That to the 1.33 minus 1 divided by 1.33, we would get the isentropic temperature to be 655 Kelvin. And if we go ahead and we plug that into our efficiency equation, we can go ahead and say the efficiency is 91% equals temperature into the the turbine, minus the actual temperature out of the turbine, divided by the temperature into the turbine minus the isentropic temperature out of the turbine. You do this math, you should find that the actual temperature coming out of the turbine is 686 Kelvin, which then if you're going to try to find the work per mass, which would be Cp times the temperature in minus the actual temperature out, you would basically, again, where Cp in this case is no longer 1, if you look it up according to temperature, you would find that it actually increased as compared to that going into the compressor, so 1.15 kilojoules per kilogram Kelvin. You would find that, again, the work per mass would be 361 kilojoules per kilogram. So again, that is basically what we're going to be finishing this video on. It's a short video, but just wanted to make sure we worked through a few example problems on the compressor process and the turbine process. Now, the next video we'll move on to looking at the whole Brayton cycle and then some examples of different combustion turbines. So at this point, we will go ahead and conclude this current video.